In section 8.2, I'm going to do a few more numerical problems involving forces acting diagonally to our coordinate system. First, I'd like to point out that the normal force is not always equal to the weight of an object. If there is a force that acts in any way vertically on an object in contact with a horizontal surface like a floor, the normal force will not equal the weight. In this case, we'll have a tension force that has a component in the y direction. And we know that this object will stay in contact with the floor, therefore it will not move vertically. And so the y forces have to be balanced, and the total upward force, which is the sum of the normal force and the y component of the tension, that equals the weight. So the normal force will not equal the weight, it'll equal the difference between the weight and the y component of the tension. And you're going to see that in the next example. In this example, we have a student that pulls a 20-kilogram box across a floor by applying a tension of 210 newtons. We're given the coefficient of kinetic friction between the box and the floor, and we should recognize that as mu k. So mu k is going to be 0.2. We're to neglect drag and determine the normal force, the force of friction, and the acceleration of the box. We'll start out as normal, where we draw a free body diagram showing the forces acting on the box. We'll have the weight force acting down, the normal force acting perpendicular, aka normal to the surface of contact, and that normal force will be up. We'll have the tension acting along the string, and because the string is at an angle, we'll have to break that tension force into its x and y components. And we'll have a friction force that acts opposite motion, in this case to the left. Before we go any further, it's a good idea to calculate the components of the tension. We're going to need that to solve this problem. And so we can take the tension force along with its components and rearrange it into a right triangle so that you could use right triangle trig, knowing that the value of the tension force is 210, and knowing that the angle with the x-axis is 26, you could use right triangle trig to find tx and ty. Alternatively, we can use the shortcuts that I introduced in section 8.1, and so I'm going to do that here. The x component to the tension will be the tension times the cosine of the angle with the x. I know the tension is 210, and I know the angle with the x is 26 degrees. So the x component is going to work out to be 188.7 newtons. I can use the similar shortcut for the y component. Here we're going to use the sine function. It's the same two numbers, just a different trig function. And we can then calculate the y component for the tension to be 92.06 newtons. Now, I do want to take a second to point out that I had to round these values off. It's very common to happen when you are doing anything involving trig. And when you round off in the middle of a problem like I've done here, it's important to always take it out a couple extra decimal places. On positive physics, you're to express all of your answers to 3 significant figures. So that's why I am taking these rounded values out to 4 significant figures each. So for part A, where we have to find the normal force, the box does not move vertically. And because the box does not move vertically, I know vertical forces have to be balanced. The total force upwards, which is the sum of the normal force and the y component to the tension, is going to have to equal the weight. The weight being, of course, m times g. So I can rearrange this to find the normal force. It will be the weight minus Ty. I can find the value of the weight by taking the mass, 20, multiplying it by g, which is 10, and then subtracting Ty, which I found to be 92.06. That will give me a value for the normal force of 108 newtons. And since this is my final answer, I can round that to 3 significant figures. Calculating the magnitude of the frictional force is pretty straightforward. We have an equation for the force of kinetic friction. It's mu k times normal force. So I just have to multiply those two values. I know the value of mu k. I just determined the normal force is 108. And so we can calculate the kinetic friction force to be 21.6 newtons. Again, I'm rounding my final answer to 3 significant figures. I'm going to need a little bit more space to work out the acceleration of the box. We are going to need 2 values from this slide. We're going to need the x component for the tension, and we're going to need the value of the friction. I'm going to need those 2 values because the acceleration is going to occur in the x direction, and therefore we're going to need to find the x direction forces. Okay, so I've cleared out some room. I've carried over the 2 values that I will need to calculate the acceleration of the box. And to calculate the acceleration of the box, I'm going to use Newton's second law, where acceleration is the net force divided by the mass. Now, it's important to remember that the acceleration is occurring in the x direction. Therefore, when we go to find the net force, we're going to look at the forces only in the x direction. I've got the x component of the tension acting in what I'll call the positive direction, and the friction force acts opposite that, so I have to give that the opposite sign. Filling in numbers. And calculating, I find that the net force is 167.1 newtons. I can now bring that value up here in order to solve for the acceleration. The mass is given as 20 kilograms, and so the acceleration will work out to be 8.36, and acceleration is measured in meters per second squared. Time for one last example. Here we have a 4,000 kilogram helicopter that's tilted as shown in the picture and is flying horizontally, which means that it's not gaining or losing any altitude. And we know that it experiences a 1600 Newton drag. We want to find the thrust that's generated by the helicopter, and we want to find the helicopter's acceleration and then describe the helicopter's speed. So just as we've done before, we're going to start by drawing a free body diagram showing the forces acting on the helicopter. There's the weight force that acts down, the drag force that will be acting to the left, which is opposite motion, and then there's going to be a thrust force that acts mostly sideways, but with some vertical component as well. Being that that thrust force acts at an angle to our coordinate system, we have to split it into its components. And we can then take the components and turn them into a right triangle. And we can use this right triangle to find the thrust. Now, the fact that it says that the helicopter is moving only horizontally, that tells me that the vertical forces are balanced. And so we know that the thrust in the y direction has to equal the weight. We know how to calculate the weight. It's the mass times g. We're given the mass as 4,000 kilograms. We know g is 10. And so we know that the thrust force component in the y direction has to be 40,000 newtons. So we know the we know the y direction force. We know the angle that the force makes with the x-axis is 18 degrees, and so we know the side opposite this angle, and we know we want to find the hypotenuse. Sine is the trig function that relates the opposite and hypotenuse of a right triangle. Sine is opposite, which has a value of 40,000, divided by hypotenuse. We can then rearrange this to solve for the hypotenuse, which is the thrust. This will be 40,000 divided by the sine of 18 degrees. And this will give us our thrust force as 145,118 newtons. We're going to need this value to solve the rest of the problem for parts B and C, but I'm going to run out of room here, so I'm going to clear some space and make a new slide so that I can finish the example. All right, in order to find the helicopter's acceleration, we're going to need to find all the forces that act in the x direction, which will include the x component of the thrust force. We can use one of the shortcuts. The x component of the thrust force will be the thrust force times the cosine that the angle of the angle with the x. You can fill in numbers. And we can determine that the x component to the thrust force is going to be 136,497 newtons. We're going to use that value to calculate the net force. I know that the net force is specifically going to be in the x direction because I know the helicopter doesn't move up and down, so the up and down forces have to cancel each other out. The net force in the x is going to be the x component to the thrust minus the drag. I can fill in numbers. The drag was given to us as 1,600 newtons. And we can determine that the net force in the x is 134,897 newtons. Now that I know what the net force is, I can simply use Newton's second law that says the acceleration is the net force over the mass. I can take the net force that I just found and divide it by the mass of the helicopter. This gives me a value of 33.7 meters per second squared. Now, for part C, we found that the net force is going to be in the positive direction, which determines the direction of the acceleration in the positive direction. And we should note that the helicopter is moving in that forward positive direction. And when an object's acceleration and velocity are in the same direction, the speed is going to increase.